And so let's start with a little simulation here. So what we have is some iron, and we're heating it up. And so when we heat it up, we're adding energy to the iron. That's kinetic energy of those molecules, and a lot of that energy is eventually going to be released to the environment. Likewise, when we cool something down like water, then we're removing energy from it. It has a lower amount of energy. If I take a warmer object like iron and put it in that colder water, you can see that energy is now flowing out from the iron into the water. And we'll talk more about this process in the next video on calorimetry and how we can measure that. But know this, if we heat something up, that means that we're adding energy to it. And so if I have two beakers and they have the same amount of water in each one, and one is 1 degree and one is 25 degrees, which one has more energy? Well, it's going to be the one that's warmer. We've added more energy to that. And so we're going to represent that as these little cubes. And so what were to happen if we were to put this warm object next to this cold object, over time we're going to see energy flowing from the warm to the cold. And so we're going to start to approach thermodynamic equilibrium. And so I have a time lapse here, and this is simply a glass of ice that's going to melt over time. And so what happens as it melts is it's adding energy to that ice. It's speeding up the molecules, and it's going to change from one phase to another. And then likewise, as we cool it down, we're going to remove energy from that system. And so if we let it run like this, we can see over about an hour and a half that's changing from ice to water. And so what's happening is energy from the surroundings is flowing into that system. And so if we were to look at the energy around the glass, it's actually decreasing. Now if we were to run that backwards and freeze that again, what would be happening? Well, we're removing energy from that system, and that energy is going to move to the surroundings. A freezer does this, and if you ever put your hand behind a freezer, what you'll find is there's heat there, and that's because we're removing heat from that system. And so a way that we measure the different amounts of energy added or released as we heat something up is using a term called specific heat capacity. And it's going to be different in each of the different materials that we have. So you can see here in gold it's going to be a relatively low number. And we measure that in joules. That's the amount of energy or the heat divided by the grams degrees Kelvin. And so the matter, or the amount we have there is important. And the temperature that we're increasing is going to be important as well. So as we heat this up, we'll find that the one that has the highest specific heat capacity, that is water, its temperature is going to change the least amount. And so we can measure how different things are heated or cooled at different rates using specific heat capacity. And so as we move phases from solid to liquid to gas, obviously we're increasing the temperature of that. But as we switch between one phase and another phase, we find something kind of interesting. If we look at the heating curve of water, what we'll find is as we add heat to it, we're going to see an increase in the temperature. In other words, the ice is going to be cold, and as we add temperature to it, it's going to increase. But what's interesting is it'll flatline for a while. And why is it doing that? Well, it's making this transition from either ice to water or water to water vapor. And so during that solid liquid transition, as we switch from one phase to another, we're actually adding energy to it, but we're not increasing the temperature for a while. Likewise, as we move from water to vapor, the same thing is going to occur. And that's because we require a certain amount of energy to switch from one phase to another. And so if we look at that same kind of a diagram, to go from solid to liquid, we have to add energy, and that's called the molar enthalpy of fusion to switch from one to another. It's going to be different in any material or substance that we have. You can see in water and iron it's going to be a different amount. The molar enthalpy is simply measured in the kilojoules per mole, so it's going to depend on the amount of material that we have. Likewise, as we move from liquid to a gas, we're going to add that molar enthalpy of vaporization, and so that's going to be a positive value. We have to put energy into that system to get that phase change to occur. Now likewise, if we go in the other direction, as we go from a gas to a liquid, then we're going to have a negative molar enthalpy of vaporization. It's the same thing, but in this case it's actually releasing energy to the surroundings. And likewise, as we go from a liquid to a solid, we're going to see a release of energy as well. The values are exactly the same, it's just going to be negative.
To continue off of what Mr. Anderson just showed us, we have our heating curve here of water. It goes from a solid ice to gas all the way up at the top. Several things happen along the way, which we've already talked about and labeled before. But as we go through the notes today, I want us to rewrite these underneath the little flap in your notes so that you can test yourself later on. And then now we're also going to add information about how much energy is required to go from a solid to a liquid and then to a gas. And at the same time, we're also going to talk about specific heat capacities of water at these three stages. So start off, heat of fusion. This is when we're talking about a solid going to a liquid, so melting, or backwards from a liquid to a solid, which is freezing. Now, if you are going one way or the other, it is the same value. It's actually 334 joules of energy for every gram of solid or liquid. If you're going backwards from a liquid to a solid, so you're freezing, it's going to be a negative number because you're removing the energy from that system. Also, we're going to talk about heat of vaporization here. This is when liquid goes to a gas or vice versa, so either evaporating or condensing. It takes a lot more energy to go from a liquid to a gas or backwards, 2,260 joules per every gram. All right, now what if you're not talking about an energy phase change and you're just talking about ice? You know, how much energy does it take to change a gram of ice by 1 degree Celsius? And that's what this number means right here. This is the specific heat capacity of ice or solid water. It's about 2.1 joules of energy for every gram to change it just 1 degree Celsius. Which means if I wanted to change it 2 degrees Celsius, I'd have to double this number. Just so happens that the specific heat capacity of liquid water is about double that. And so liquid water is 4.18 joules of energy for every gram of liquid water just to change it 1 degree Celsius. Now, we're going to use those numbers in a couple of examples. Example 1, we have a cup of coffee, weighs about 130 grams, and it's going to cool from hot 70-degree coffee down to 20 degrees Celsius, about room temperature. And the question is, how much energy is the coffee releasing to the air in the cup and everything around it? All right, we're going to use the graph here and the information we have in the problem. For example, if we're starting with really hot coffee, 7 degrees Celsius, it's going to be pretty high up on the liquid line here in the center, and it's going to cool. So that means it's going to go down the graph to a colder spot, 20 degrees Celsius on that same line. It doesn't change phases, so we're not going to reach this plateau. It's going to stay in the liquid state of matter or phase this entire time. The real question is, does this 50-degree change, so 70 minus 20, take a lot of energy or a little energy? And so we have to think about, first of all, what kind of change is happening. Are we just changing temperature, or are we changing phase? If we're just changing temperature, which is this case right here, we haven't hit any of the plateaus, we're only going to be using heat capacity. And this time we're using liquid water, therefore we'll use the heat capacity of liquid water, which is 4.18 joules for every 1 gram to change it 1 degree Celsius. And that's only if you have 1 gram and you're only changing it by 1 degree Celsius. But what if instead we wanted to change 130 grams? So we're going to set up a proportional problem. You'll see I kind of already started. We want to know how much energy it would take now, instead of just 1 gram, to change 130. And not only by 1 degree Celsius, but by 50 degrees. And so you set up the proportion problem so that you can solve it by cross multiplication. You'll see here we're going to cross multiply 4.18 joules times 130 grams times 50 degrees Celsius. And then the x gets multiplied by 1 by 1. Which means if you type that all out in the calculator, you should end up with a final answer of 27,170 joules of energy is required, anyway, for 130 grams to change by 50 degrees Celsius. All right, number 2, a little bit different. Now, let's say we know how much energy, 60 kilojoules, in fact, is transferred to a 475 gram bucket of water, and it's starting at 25 degrees Celsius, and we want to know this time, though, if we add that 60 kilojoules, what's the final temperature going to be? So we need to find temperature change ultimately, but first we got to decide where we are on the graph. If we're starting at 25 degrees Celsius, it's going to be pretty low on the liquid water line. And then we know, because we're adding energy here, that it's going to increase. It should get warmer. And so that means we're going to be going up the line. By the way, 60 kilojoules of energy is 60,000 joules of energy. So all you have to do is take your original number and times it by 1,000, or add 3 zeros to the end, and you'll have joules, which will fit our equation nicely. Let's set up our proportion problem, keeping in mind that once again, we are stuck only in the liquid phase, so we should only use the heat capacity of liquid water. It's the same number as before, 4.18 joules over 1 gram times 1 degree Celsius. But when we set up our new proportional problem, we know the energy, and that's going to go up top. That's at 60,000 joules. And we know the grams, 475. What we don't know is how much it's going to change. We know it starts at 25, but we don't know what it's going to go to. And so by solving for x there, using our cross multiplication, we end up with an equation like this. 60,000 times 1 is easy. But these two numbers times x, not so much. So you will have to do a little bit of dividing here. 60,000 divided by 1,985.5, which will end up giving you 30 degrees Celsius of change. So if we know it's changing 30 degrees, and we know that's an increase, then we must be taking that 25 degrees Celsius from the original part of the problem and adding 30 to it to get our final temperature of 55. And finally, example 3, if you have 540 kilojoules of energy, and that's transferred to kilograms, 2.5 kilograms of water at its boiling point, what fraction would vaporize into the air? So what we're asking here is how much, or what mass amount is going to turn into a gas. That's what vaporize means. And so if we're vaporizing and we're starting at the boiling point, which is about 100 degrees Celsius, and it's going to vaporize, we're going to stay on this plateau. We're going to see a phase change this time. Phase changes means something a little different. Instead of heat capacities, we're going to be using heat of vaporization. And even if it was going in the opposite direction, we would still use this value. And that's a pretty big value again. It's 2,260 joules of energy required to change a gram. We're going to take that energy calculation that we converted from 540 kilojoules of energy, put that at the top. What we don't know is the amount that we are going to be changing. We're going to do some cross multiplication with our proportional problem. And by doing this, we come up with an equation like this, which we'll have to do some more dividing. So if you take 540,000 and divide it by 2,260, you're going to end up with 240 grams, which ultimately means that this amount is being vaporized. However, it wants to know what fraction out of 2.5 kilograms is actually being vaporized. So in this case, this is in kilos again. So if you have kilos times by 1,000, or add some zeros, and you will get your grams. And then we're going to figure out fractions. So if we have 240 out of this 2,500, you just got to divide the lesser by the greater, and you end up with 9.6%. So what this means is 9.6% of the original amount of water that we had is turning into a gas and vaporizing into the air.